Okay, now you should see my presentation.
Perfect, we see it.
Okay, so thanks for the introduction and the invitation to this workshop. It's pretty interesting seeing a lot of people actually sharing more or less the same idea and the interest. I will talk about mostly controls that we design here at the RES Lab, and all my activities in Wearable Exosuit that is mostly dedicated to upper limb, because this one is, I would say, my expertise. So I work in the RES Lab. My lab stands for Assistive Robotic and Interactive Exosuit. The lab is mainly dedicated to hardware design and control design, with different topics that range from rehabilitation to assistive device intended for human augmentation. And in fact, I have 3 pillars of research that is mostly haptic and robotic rehabilitation, from which I started my, let's say, career in the past when I was a PhD student, then intelligent actuation design. Today, I will mostly focus my presentation on human augmentation and wearable exosuit. Let me start with quite an interesting pictures of Ralph Mosher that in 1967 wanted to design his own exoskeleton. At the time, probably he was the pioneer in this kind of field, and he defined an exoskeleton as a symbiotic unit with the alacrity of man's information and control system coupled with the machine's power and ruggedness. Considering the machine powers and ruggedness at that time, there was the rise of automation, probably he had all the power that he wants. In terms of symbiosis between this system and the user, unfortunately, he was not so lucky. I would say that that kind of system was extremely hard to control. It never worked, yet it was a pioneering example from which exoskeleton and design in wearable robotics started at that time. And over the years, of course, these things change. We have, let's say, a gradual shift toward rigid robotics that incorporates the theory that comes from classic robotics and automation towards systems that are, let's say, more lightweight and made also of different materials that can be clothes. I don't want to discuss about exclusion of rigid exoskeleton because they are arriving the exosuit. I think of them more as a complementary, let's say, technologies, also because exosuits has some limitation that are exactly the complementary non-limitation that rigid exoskeleton have. But let me start talking about the exosuit. It's something that started not many years ago. I would say that probably the pioneering lab was the one of Connor Walsh at Harvard. It's the Biodesign Lab. He started actually this research when he was already at MIT with huge hair. And we have several examples of wearable exosuit. At the beginning were mostly thought for augmentation of lower limb. But there are several examples also for what concern upper limb in a variety of fashions, embedding actually different kind of actuation. And I will discuss what kind of actuation are mostly used in wearable exosuit. I designed my own stuff in my lab. I started my career doing research in stroke rehabilitation, mostly on upper limb, and I'm still staying on upper limb, but not with rigid robotics, also right now with wearable robotics. And let me talk about the 3 pillars that are mainly the 3 pillars on which the entire exosuit design is sustained. I would say, I'm not going to talk about ergonomics because after me there will be people that are much more experienced, that are Sasha and Patricia, but I will talk about actuation and control. And what to say about actuation? Well, for actuation, we have several kinds of actuation that are used right now in exosuit, starting from the inspiration from the musculoskeletal system that, of course, still represents the better actuation system so far present in nature with a fantastic power-weight ratio. There are electromechanical actuation, pneumatic artificial muscles. Electromechanical actuation uses twist and spring, shape memory alloys, and pneumatic interference actuators. My experience mostly is based on electromechanical actuators and all the part related to control that mainly comes from general haptics application and force control. What was the first example of this kind of actuation technology? Well, it started from the Harvard Biodesign Lab with Connor Walsh, And it was mainly consisted in a layered control to detect the gait events, transform these gait events into a force profile, and then a trajectory that was communicated at the ankle or at the hip. The system actually provided quite an extremely nice example on how to use electromechanical actuation to reduce the metabolic cost, not only during walking, but also during running. And that one was, let's say, and it is right now, in my opinion, the state of the art for tendon-driven actuation for lower limb. Now, for what concerns the upper limb, there are not many examples. I tried to give my, let's say, contribution in this field. I started design, for example, exoglove system. It's a bit noisy, the actuation that are tendon-driven. The control is mainly based on an amplification of velocity of the finger, because there are embedded sensor inside. And as you can see, the system responds quite well. Okay, decreasing the electromyography of the hand, and so far. We tested this kind of control, an extremely simple control, also from a stroke or spinal cord injury population. And we actually had decent results. This person was absolutely not able to grasp anything in this test that was the box and block test. That is one of the most widely used tests in spinal cord injury and stroke. He demonstrated that mainly the use of this device was quite beneficial. We wanted to explore controllers that are a bit more complex. For example, controllers that are based on electromyography, but not using electromyography that is mostly based on proportional signal. We have a collaboration with the DLR, with Claudio Castellini and Marek Sierotowicz, that is one of his PhD. And we wanted to use a stable myoelectric control for this exoglove that use nonlinear incremental learning. So you can use machine learning also for this kind of things. This is a very preliminary example. Hopefully, next year probably I will be able to show a bit more results. But the system is able to classify between different posture of the hand, mainly driving 2 degrees of freedom. And after the movement has been classified, you can online also modulate the force that the person can want to exert on the object that wants to grasp. The problem of this kind of application, especially with people affected by stroke or spinal cord injury, is that if you have a glove, then putting the hand of this person inside the glove is not very easy. So we were thinking about how using disposable 3D printing system to create, based on anthropometrics of the subject, gloves that are ready-made in 1 day of production and assembly. Completely disposable, you just print them, by a normal 3D printing machine using flexible material. You can mainly sew some part of the distribution for the actuation on the glove. And then after that, the glove is extremely simple because you can connect the transmission by magnetic clutch and is able to be used. Okay, completely scaled in terms of anthropometrics on subjects that are actually requested this kind of system. You can bring it at home and then eventually reusing during rehabilitation. Now, let's go a bit about a bit in details about what concerns the control. So let's say that mostly the type of controller that are used for exosuit are 2 types: force-based position control and admittance-based force tracking. While force-based position control is the one that is most widely used for lower limb control, for upper limb control, mainly admittance-based force tracking is used. You know why? Because while for lower limb, you are able to classify the walking phases, for upper limb, you have a manifold of dexterity that is much wider. So you need to identify the force reference to be sent inside the force control, admittance or impedance control, and then driving the electromechanical actuation. Now, what kind of force reference are you sending there? How you can detect? I have my approach. The idea, of course, is try to instrument the wearable exosuit as much as you can, but not hampering the mobility of the person that is wearing the exosuit, and then try to decode the human motion intention, compensate for the non-linearities that you have inside this flexible system that are mainly backlash in the actuation and high static friction when the cable is pulled inside the Bowden sheet. The first idea was designing a quite complex controller that, I mean, let's say worked decently well, but it was extremely complex because it was a layered controller we called a hierarchical cascade control, mainly with the first layer that was mainly dedicated to the detection of motion intention based by a simple dynamical model of the arm, and then compensation of backlash and friction before driving the motor. The system works decently well. I mean, as you can see here, the subject is requested to move in concert with this simplified avatar, and the tracking of the torque at the elbow was online estimated by means of this hierarchical system. Respect of using the exosuit and non using the exosuit, of course, you have a significant reduction in terms of electromechanical actuation, okay? Yet there are some limitations. And the idea then was, instead of using a simple biomechanical model of the arm, can we embed something a bit more complex using eventually an open sim simulator running inside the controller? So the idea was having a model that was completely scaled on subject anthropometrics, having an outer loop that mainly consists in an assistance estimation, an inner velocity loop to drive the actuation, and then a positive feedback to simplify the friction compensation inside. How this system worked? Well, decently well, in the sense that was quite responsive. Of course, it does not adapt to the external environment because the gains, once are set, yet it was quite responsive. What are the limitations of this kind of controllers? Well, the limitation is that the faster you move and the less accurate will be the force and the trajectory that will be input by the exosuit at the elbow level. Here you see an example. If I move, for example, at 42 degrees per second, the black line that is the trajectory of that I am replicating with the exoskeleton on, or the exosuit on, has a delay respect to the desired motion. If I increase the velocity, of course, I have a higher delay. What about saving biological torque? Well, also in this case, biological torque is saved in a higher percentage if the movement is within the bandwidth of the exosuit. So it means that if I move very fast, the system still allows me to save more or less 50% of my biological torque when I am manipulating a load that, of course, will not saturate the system. Yet, the faster I move, the lower will be the assistance in parallel of the exosuit that I have. Another interesting thing, of course, is that I have a decrease in muscular signal when I use this exosuit, so I have a delay of the muscular fatigue. Now, you have several advantages with this kind of admittance controller. You delay the onset fatigue, you reduce biological torque and muscular effort. Yet, there's no symbiosis, not yet. And the problem mostly is due to the fact that without putting biosignal in the loop, the responsiveness of the system itself cannot match the one of our biomechanical system. How can you do that? How can you solve this kind of problem? Well, you need to implement a control that is able to predict the dynamics and make the response of the exosuit as transparent as possible. You can do it by improving this kind of aspect. For example, by creating what is called an adapted model-based myoelectric control that we try to investigate when I was, at that time, I was in University of Twente before joining Heidelberg University. And we put together the effort with Massimo Sartori, that is an expert in online biomechanical modeling and torque estimation, biological torque estimation. We closed the loop on biosignal. And mainly we created what is called a myoprocessor. That is more or less a processing system that detects motion and EMG. And then with an extremely accurate biomechanical model, transform this computational effort into torque that is then communicated in parallel to the elbow of the subject that is wearing the exosuit. How does it work? Well, it's quite responsive. The initial system that we tested was tested on 7 electromyographic probes, of course, many electrodes, but the estimation was extremely fast. we have estimation in the order of 60 milliseconds. And that one, of course, improved the performance for what concerns the symbiosis of the exosuit. So once I opened my lab in Heidelberg, that was almost 2 years ago, we wanted to design a completely embedded system working on an Arduino and an NVIDIA Jackson using mainly MATLAB Simulink to run exactly the same controller, but this time using two myoelectric sensors, so mainly two probes. And how it works, the system? Well, the system works pretty smooth. You can see here, for example, the difference in lifting a weight with and without the exosuit. If you look at the biceps electromyography, of course, is much higher without the exosuit rather than the exosuit. And of course, the system was extremely responsive. Apparently most responsive than the admittance control force-based, okay, without biosignal in the loop. Let me go ahead. So, and let's say that this myocontroller seems to be completely, superior, outperform the force controller. Is it true? Can we do, even if we have this real-time control that is very fast and accurate because I have biosignal in the loop, is it true that it's completely superior with respect to a simple force control? Well, first of all, for clarity, for sake of time, I didn't introduce all the calibration process that you need to run a myoprocessor. You have an extensive calibration process. You need to use motion analysis, maximum voluntary contraction, while only using the force control. You just measure the anthropometrics and then you input in the model. You don't need to run any kind of extensive calibration. So let's compare the two controllers. Let's see who's the best solution. Let's see how they behave in a dynamic condition when they are perturbed suddenly by an external perturbation. And let's see who moves more symbiotically with the wearer. We design exactly the same controller, but including both the controller in the loop. Of course, one excludes the other when they work. They cannot work in parallel. So the dynamic arm model and the myoprocessor. And then we tested these two algorithms, stressing them for what concern all the performance in actuation and delivery of assistance. Well, let me tell you that between the two controllers, in terms of actuation, let's say that, that the muscles, they have an electromyography. So when the electromyographic signal arises, the muscle itself, that is a biomechanical system, has a delay. This is called electromechanical delay. That is about 60 milliseconds. I would say that the myoprocessor stays below the electromechanical delay. As soon as you fire the muscles, the system intervenes before 60 milliseconds. But yet, a very strong and a very optimized force controller interact with the user in 150 milliseconds. Here we have, despite the significant difference, an actuation response that is absolutely comparable, at least in terms of haptic rendering. What about if I stress the two controllers in, for example, a very accurate motion, pick and place, and a very dynamic task, throw and catch between two actors, one with the exos and the other without, and then if I input a sudden perturbation that can be a step response or a load that is falling down. Well, the step response tells me, for example, that it's true that the electromyography is faster in providing assistance when I perturb the subject. And the subject is not able to see what is happening, otherwise it will co-contract. But it's also true that the dynamic arm system stabilizes much better than the myoprocessor. So why? Well, because the dynamic system, the force control, has a damping that is intrinsic, while when you have EMG in the loop and when you perturb so suddenly, we think that the noise that is produced by oscillation and sudden activation of the muscles results in a settling time of the system itself that is slightly larger. Here we're talking about 1.5 against 2 seconds of stabilization in the settling time. What about pick and place? Well, here the interesting thing is that in both the controller, the person were absolutely able to smoothly move. And let me see if I can make you hear the actuation noise. Okay, but the interesting thing was that if you look at this red line in here, that is the power that is communicated by the torque that is communicated during the myoelectric control, depending on the weight, the actuation tends to increase independently on the gain that we set. So it means that the electromyographic signal that use the same admittance control as the force controller mainly increase the assistance depending on the external load. And this is something adaptive, this adaptivity, that a normal force control doesn't have. And what about unimanual and bimanual catch and throw? Honestly, we didn't find absolutely any problem and any difference between the two controllers. They mostly respond at the same time. They provide more or less the same assistance, statistically speaking. We made some calculation in the power exchange. So it's true that the myoprocessor for certain kind of things, having the biosignal in the loop responds much better, but it's also true that the dynamic arm controller, once you get measure of the arm, you put the exosuit on and it will work. So what is the difference between the two? Well, of course, if you have, and if you want to use this kind of approach in clinical application, you need to detect the residual voluntary motion, and then you need to put biosignal in the loop. But the dynamic arm model is something that can be extremely useful when you want to have off-the-shelf application, for example, industrial exoskeleton. So this is a question for the audience. Is this task myoelectrically actuated or force control actuated? This is something, this is my question for the audience, then the audience will have many other nasty questions. So myoelectric in the loop or not? Let's go ahead. I'm not working only in control, I'm working also in industrial exoskeleton. I have quite strong collaboration with two companies, one for lower limb, one for upper limb, but with two different completely applications. I am trying to employ smart materials with strain stiffening capacity in soft wearable exosuit for lower limb. And I collaborate closely with a company that is called Unich, with the help of Matt Millard and Lisette Slot, that are two biomechanics, extremely skilled both computationally and experimentally, and a colleague of mine, Christine Zellhuber-Hunkel, that is a person working in material science. We don't have results. We are actually thinking about how to use strain stiffening material for avoiding what is called flexion relaxation. That is something we can discuss later if there's time. But for what concerned Comau, with Nicola Vitiello and Simona Crea, actually, that presented probably an hour ago, we are considering of, no, actually, we already have an hybrid system that consists in a soft and rigid exoskeleton, because there's a layer in exosuit and a layer in hard exoskeleton, and active or spring-loaded mechanism. So we have mainly a sort of add-on system that is based on inertial measurement unit and force control, no myoelectric control, in order to actuate the system for what concern biceps and triceps. And then, and this is probably the first example right now in hybrid assistive exoskeleton / exosuit, using electromechanically actuated assistance that is completely embedded, relying on a musculoskeletal modeling, but without including biosensors inside, and a spring-loaded system that is commercially available. This was the last slide of my presentation. I would like to thank, of course, my team at the Aries Lab and all the collaborators and the company that actually sponsored my research here in Heidelberg University. Thank you very much.
Thank you, Lorenzo. So at this point, we'll open it up for any questions. So again, you can feel free to ask in the Q&A. And if you are a panelist, you can also just speak up if you would like.
Yeah.
Oh, it looks like I have a question from Xiao Fang. And they ask, is there any benefit to add online impedance adaptation to control, or adaptation control to elbow and finger exo control?
But of course, if it's adaptive, it's much better. Now, how to make it adaptive? It depends. There are, of course, all this algorithm right now of machine learning, reinforcement learning. I have to say that for what concerns machine learning, I am a bit artificial deficient in the sense that I am not very much into machine learning. For what I know, at least in my field, there are a lot of problems because you need a lot of data to train, the system itself, especially if you are considering not much, the lower limb, because lower limb and the adaptation of lower limb and optimization of gains to reduce metabolic consumption is something that has been done. Steve Collins, Connor Walsh, Karzelik as well, they have their own algorithm and they demonstrate it. For upper limb, unless you don't have a highly repetitive task and you can train the network, guys, if you want to just someone that takes boxes and do it, thousands of times, you can do it. I would rather prefer an adaptive systems that, for example, modulate the gains depending on the task that I'm doing. And this is, of course, something that you can store in the memory of the control system. You might want a classifier eventually. Well, I'm raising, for example, a big box. So my arms are quite separated. Probably it's heavy. Let's tune the admittance control a bit higher. Let's increase the proportional gain and the system will push more. Or it's a smaller box. I'm pretty sure that probably it's not heavy unless you don't have depleted uranium inside. And then, but that one you cannot train. You should have probably a radiation detector to tune the gain of the impedance controller. But this is, in my opinion, the maximum of adaptation right now that we can have in this kind of application. Okay, especially in the industrial scenario, you want something that you really put on. Hey, you want to use it, and I want to use it without any calibration. Okay, this is at least what I think. I'm a very simplistic person.
Serena. Pointing to the raised hand, that's the new one.
So I have a big question that is linked to some things that you said and also to some of the things we evoked in the first part and also in the panel discussion. So because you presented a lot of controllers from like the simple admittance controller to something that uses biosignals, a lot of stuff that is complicated. And so in light of what we evoked in the panel discussion and before, the fact that it's easier for a human to learn how to interact physically with a simpler system. Do you think there is like there can be an advantage in this light to have a simpler system that maybe works not very well, like with an admittance controller that maybe have tunable gains, but or you still prefer?
Let me make a parenthesis.
Yeah.
The admittance controller and the myoelectric controller probably was my fault. I didn't explain. They both use the low-level controller that is the same, but one has an inertial measurement unit that detects the configuration of the three-dimensional configuration of the arm and then give the assistance in order to make the things transparent. The other one has inertial measurement unit plus EMG. The EMG, what gives you is a wider range of assistance, but the complexity is very similar. It's a pure force control in which you detect a motion, you send the force, and it comes out with a velocity, admittance.
Yeah, because I was thinking that including EMG, like in the controller of an exoskeleton that is deployed, like on clothes or etc., it's very complicated.
I'm not very much into EMG also because, there are people much better than me in biosignal analysis and so on. This is, and in fact, I have to say that, my experience with model-based control was coming from a collaboration with someone that is much more expert in this. It was Massimo Sartori. Of course, we were the first including this kind of control on exosuits. Then, since I'm an engineer and not a neuroscientist or a neurophysiologist, I say, well, how many EMG are we using? 6, forget it. Let's use 2. And still works pretty decently, especially also for what concerns the hand. Now, I didn't show, but we have a complete system. Also the shoulder, probably. Let's see if it will work. And you have, 5 EMG. And 3 IMU. You want to use EMG in industrial scenario? No. You want to use it in clinics? Yes, because eventually in clinics, especially in determined case, when you don't have a detection of voluntary motion control due to the fact that these people, they have a very low firing signal, then you need to check if the EMG that you detect are useful to drive the system. But still is an open question. I cannot respond, I cannot reply.
If I can quickly comment on this, I think the problem with the EMGs are not the EMGs themselves, the way we are measuring them. Because everything is done through surface electrodes, and they are subject to, let's say, drift, and this, their position can change. But in an eventual case that we can have, implanted chips that basically you can easily put them anywhere you want. This can be. I mean, it looks like science, sounds like science fiction at the moment. But one day, if that happens, we are ready. We have control techniques.
Elon Musk and BrainGate next time, not me.
No, actually, this is quite doable in let's say, for instance, in FES, in functional electrical stimulation. This has been the way you put the electric stimulators in intramuscular. But I think the EMGs, the way we are measuring it, is not going to work. Sorry.
So with the FES, the EMG control is completely overrated.
No. I was mentioning the sensors. Of course, EMG and FES, they collide.
I mean, there are people doing EMG and FES. Polytechnic of Milan, Emilia Ambrosini and the group of Alessandra Pedrocchi. To be honest, I'm not an expert in FES. There's this idea of firing the muscle and then getting the EMG and then assisting via a robotic system.
Sure.
But I cannot comment on it, honestly. I would speculate.
Of course. And Lorenzo, I wanted to mention something. Of course, it also depends on the context, because when it comes to paraplegics, there's no EMG. When it comes to industry, EMG could be a good option. Of course, we cannot have a really unified control approach saying that this is going to work every time, unless you don't want to include any human intention in it. But when it comes to human, let's say, detection and reactive actions, probably we need to find a way of the best ways of how we can get human movements or intentions. And the way, of course, the EMGs are measured now, I think the best way to get them is to switch controllers, not a continuous control, but more of a discrete control. That was, this is actually, the work also we did together, Lorenzo, was mostly in this direction.
Quick follow-up question from the audience, and this will be the last one. We'll move on after this. But from Michael, asking about the, sorry?
You didn't reply to my question. It was EMG controller or force control, the video that I showed when they were throwing the snowball?
Yes, we didn't have the, I mean, people can feel free in the chat. So while we're asking this last question of our speaker, you can answer his. We'll tally results. Do you consider EMG an appropriate measure for control with those who may have abnormal muscle activation patterns due to something like a stroke? Or have you looked at actual patient populations at all yet?
I didn't get the question. What is the best patient population that I would target?
Oh no, it was stating that do you consider EMG an appropriate metric for control or event detection to be used in rehabilitation for individuals who have abnormal muscle activation patterns?
It's hard to say because there's a huge variability, and to be honest, right now at the moment there are no specific guidelines. So I mean, for people that are neurologically intact, it's very bad to say, but they don't have, central motor system damage, like, for example, spinal cord injury, and they have the peripheral damage. Let's say that a correct between comma or a more reliable EMG signal can be detected, but it depends on the level of spinalization. For what concerns stroke, hard to say. Do they have maladaptive plasticity? Do they have, the central motor area that is completely gone? And then what they are firing, if eventually there is a motor evoked potential, but this is something that we don't know. I mean, it's variable. At least my experience in stroke, with the few papers that I succeeded in publishing in stroke, Was like, hey, let's play the statistics. Let's see.
Yeah. Awesome. All right. So we have both force EMG guesses, or I should say answers.
And the winner is force control, no EMG. Absolutely no EMG. That one was completely force control. Of course, you know, pumped up, let's say, tuned like an American car, a muscle car, but it was force control.
Awesome. Well, thank you very much, Lorenzo, for your talk.